Hey Geometry, welcome to our third section of probability. In this section we're going to get into compound probability. So compound probability is the probability of two or more events occurring. The probability of two or more events. So for example, we roll a die and toss a coin. And we're interested in, a couple of things happening out of that. Rolling a die and tossing a coin. We do each one individually. So I'm going to call that like simple probability, and then we get to compound probability. So an important thing with this is, are those events related? So independent events are independent if the outcome of one event does not affect the likelihood of the other event occurring. So like rolling a die and tossing a coin. Given independent events, we call them A and B, we'll just refer to those as letters, the probability of both events occurring, A, and this little symbol here is intersect, A and B, is what that means. So that is an and or / intersection. Another way of referring to that is the product of the probability of A and the probability of B. This is only if we're dealing with independent events. So when probability of when A and B are independent, the probability of A and intersect B is equal to the probability of A times the probability of B. We can just multiply those together. So used for questions 1 and 2, if the spinner on the left is spun, then a letter from the word bingo is chosen at random. Find each probability. The probability that it is less than 7. And so that would include 6 on down to 1. So that's going to be 6 out of 10, assuming this is a fair spinner, which we'll assume it is. 6 out of 10 times the probability that we get a B, which is 1 out of the 5 letters. So we multiply those out and we get 6 out of 50, which we can reduce to 3 out of 25. The next one, probably that we get at least 3. So that would include 3 on up to 10. So that is 8 out of the 10 numbers. So 8 out of 10. And we could reduce that fraction first if we wanted. And then a vowel. So that would be the I and the O, which is 2 out of 5. And so if we do 8/10 times 2/5, we get 16 over 50, which of course can reduce. If this fraction could reduce, then this one will be able to. That reduces, can cut it in half to 8 over 25. For that probability. A die is rolled 2 times. What is the probability of getting a number that is greater than 4 on both rolls? So when you roll we're assuming a 6-sided die, a number greater than 4 would be 5 and 6. So that's 2 out of 6 times 2 out of 6, which is 4 out of 36, which we can divide both those by 4, and we get 1/9 for our probability. A number is chosen. A number from 1 to 20 is chosen at random. Then a coin is flipped. What is the probability of choosing a prime number, then getting tails? So again, our prime numbers start at 2. So our prime numbers would be 2, 3, and we're going from 1 to 20. 2, 3, 5, 7, 11. Sorry, I almost went to 9 there. 2, 3, 5, 7, 11, 13, and 17. And 19. Sorry, I almost got there. So there we have 1, 2, 3, 4, 5, 6, 7, 8 favorable outcomes. So 8 out of 20 is our probability of getting a prime number. Then getting tails, that's just times 1/2. And so we get 8 out of 40, which of course we can reduce. We can divide both of those by 8 and get 1/5. And so all of these are independent, where one outcome has no effect on the others. You could go ahead and try and do these, speed ahead and do these on your own, pause and see if you get them right, but I'll continue on here. A card is chosen at random from a deck of cards, replaced, and then another card is chosen. What is the probability of choosing a diamond both times? And so 13 out of 52 if you want to do big numbers and then reduce, but it ends up just being a 1/4 probability. There's 4 suits, and so it's 1/4 times 1/4 for both of those. So it ends up being a 1/16 probability you get a diamond both times. A month of the year and a day of the, and that one, by the way, it is really important that the card is replaced and then another card is chosen. If you didn't replace and then, and it probably should say, and shuffled, then it would actually move into our conditional probability situation. A month of the year and a day of the week are chosen at random. What is the probability of choosing a month starting with J, then Wednesday? So our months that start with J, we've got 3. We've got January, June, and July. So 3 out of 12. And then picking Wednesday, 1 out of 7. And so if we multiply that out, we get 3 out of 84. And that actually does reduce. We can divide both those by 3, and we get 1 out of 28 for that one. A coin is tossed 4 times. What is the probability of getting heads each time? That would be a 1/2 times 1/2 times 1/2 times 1/2. All right, so that's getting compound more than just 2 events, but so that's why it's 2 or more. We could also have done this just 1/2 to the 4th, and so we get 1 out of 32 for this one. And I didn't multiply that right. 1 out of 16. Sorry, 32 would be to the 5th. Sorry, 1 out of 16. 2 times 2, that's 4 times 4, yeah, 16. 116. Vera guessed that on the last 3 questions of a multiple choice test, if each question had 4 answer choices, what are the probability that she got all of them correct? So the probability that you got 1 correct is 1/4, and so then the probability you get the next one correct as well, it's independent, is 1/4 and 1/4. So 4 times 4 times 4, we get 1 out of 64 for that probability. All right, a couple more examples of this one. There are 14 girls and 11 boys in Mrs. Haynes' homeroom. There are 9 girls. So there are 9 girls and 15 boys in Mr. Jump's homeroom. If a student is chosen at random from each class, what is the probability that they are both boys? So the probability of getting a boy from the first set is 11 out of, we add both of those together and get 25. And then the next one, there's 15, sorry, not a plus, but a multiply, times 15 out of adding those together, which is 24. If we multiply those out, we get 165 out of 600, which reduces to 11 out of 40. All right, and then this last one with independent probabilities. Christian is guessing the 4-digit code on to his parents' garage door opener. What is the probability that each digit is greater than 5? So this is assuming he's actually guessing like randomly, of course. So greater than 5, so that's 6, 7, 8, 9. Those are our digits. So 4 out of 10, and it's going to be 4 digits. So we're going to do 4 tenths times 4 tenths times 4 tenths. Of course, we could have just done 4 tenths to the 4th power. If we do that, we get 256 out of 1,000, which is a 16 out of 625. For that, probably you could do the decimal or percent for that as well if you wanted to. All right, the next one, dependent events. So events are dependent if the outcome of one event does affect the likelihood of the other event occurring. Given dependent events A and B, the probability of both events occurring, probability of A intersect B, A and B, is the product of the probability of A and the probability of B once A has occurred. So when A and B are dependent, the probability of A intersect B is equal to the probability of A times the probability of B given A. Another way that you'll actually see this written is there's a shorthand notation. It's B, and you do this vertical line, and that vertical line means given. You don't have to know that, but it's a nice shorthand notation for this. So for the first few questions, a bag contains 3 blue marbles, 10 green, 4 yellow, and 8 red marbles. And so, of course, we're going to need the total number of marbles from this. So we've got 3, 13, 17, plus the 8 more gets us up to 25 total marbles in the bag. So we're going to need that. We want to know the probability we get a red, then a blue. So the probability of getting a red is 8 out of 25. But then the probability that we get a blue, there are no longer 25 if we're not replacing. So a lot of times we draw end without replacing. Since that's key there, not replace. So that makes it dependent. We're now out of 24. And then the probability of getting a blue is 3 out of 24. It's slightly more likely now than it was initially. It was originally 3 out of 25, but now it's 3 out of 24. The probability's gone up just a little bit. So we multiply that out, we get 24 out of 600. That probably does reduce to 1/25th, and you could get the decimal or the percent. green and then yellow, so that would be 10 out of 25, and then yellow, we are now out of 24, so there are 4 still yellow remaining, and so it ends up being 40 out of, and this is the same denominator, out of 600, which reduces to 1 out of 15 for that one. Both red. So first red is 8 out of 25, but now, and so we're going to multiply, this is now out of 24 remaining marbles, but there are actually only 7 red left because we've removed one of them. So 8 out of 25 times 7 out of 24. If we do this, we get 56 out of 600, and that one reduces to 7 out of 75, or you can find the decimal or percent. And then both yellow, so this is 4 out of 25 times 3 out of 24. Once we take away a yellow one, there's only 3 left out of the remaining 24, and so we end up with 12 out of 600, which reduces to 1/50th, which is, I guess, 2% or 0.02. For this next few, after the completion of a race, 75 runners were asked if they ran a personal best time and if they trained for the race. Of those surveyed, 22 said they had personal best time and 46 said they trained for the race. Of those that said they had a personal best time, 18 had trained for the race. If 2 different runners in this group are chosen at random, find each probability that both runners trained for the race but did not run a personal best time. So the first thing that we want to do is find the probability that I'm going to write this out this way. We want the probability that they trained and did not run a personal best time. So, and not personal best. So that's ultimately what we're interested in. The way we can get this is we can figure out the probability that they trained for this one. And so the probability that they trained was, let's see, 22 said they had a personal best time and 46 said they had trained for the race. And then of those who said that they had the personal best time, 18 had trained for the race. If the 2 different runner groups, I think I might do this one backwards. So hold on, let me turn this around. All right, sorry, I was going about this one the wrong way here. Forgot about the fact that we're choosing 2 runners. So overall, both runners trained for the race but did not run a personal best time. So we have 46 that trained for the race. Of those 46, 18 got their personal best. So 18 of those 46. That means if we do 46 minus 18, that leaves us 28 that trained but didn't run a personal best. And so that would be 28 out of 75. And then the next individual, if we're looking for the exact same thing, it's 27 out of 74. And so if we multiply that up, we get 756 out of 5,550 possible choices there, and that reduces to 126 out of 925, and you could do the decimal or fraction if you wanted as well, decimal or percentage. All right, and then the last one runner had a personal best time and the other runner neither trained nor had a personal best time. So the personal best, that was 22 out of 75. So the first person is 22 out of 75. The next person is out of 74 remaining, and they neither trained, so they're not part of the 46. So if we do 75 minus the 46, that gives us 29. And then also, so that's 29 that didn't train, but a few of those who didn't train actually got their personal best. So out of the 22 that got personal best, 18 trained. So that means 4 got their personal best without training. So I subtract another 4 and get ultimately 25 out of 74 for that second probability, because we haven't removed anybody from that. That's still 25 over 74. And so that ends up being 550 out of 5,550, which reduces to 11 out of 111. And you could do that again, that as a decimal or a percentage.